Does anybody have any questions from the last class that they'd like to bring up before we get going? So we want to throw error bars on sample statistics. And that gives us, once we do that, I guess maybe even a better symbol here would be error bars plus sample statistics equals the estimates on the population, right? In other words, population parameters. Right, so what we learn to do is, the error bars, we abbreviate that with the symbol E. And this, like a sample statistics that we did yesterday, would be the average or the mean, right? And that gives us the population parameter, which would be the actual average. I guess plus or minus would be the more accurate way of doing it. And what we learned yesterday, so there's three types of error bars in chapter 7. What we learned to do yesterday, let's call that a type 1 error. We learned that if you know the standard deviation of the population, you can use this formula here. Use Z-scores over the square root of your sample size, and that would give you your error. That's what we did yesterday. And the conditions for using this, and this is what it shows on your formula sheet, is that you have to know the standard deviation of the population, and that's rare, right? You have to have a very large sample to do that. In this course, and again, according to the central limit theorem, another condition where you can use this, and we used that last time, is if your sample size is greater or equal to 30, then again, according to the central limit theorem that we learned in chapter 6, and according to it doesn't really matter what your distribution is, you can kind of approximate this. If the sample standard deviation can be approximated to be the population standard deviation. And that's why we were able to use that yesterday. But what if you have a smaller sample size? And that's what we're going to learn how to handle today. In other words, it's kind of a type 2 problem. That's how I call it. And that's the errors. I'm going to teach you how to use something called a T distribution or a T-score distribution. And the formula is essentially the same. And again, this is for situations where this is unknown. But again, your sample size is less than 30. But the important thing is that this is known. And you can always calculate this, right? And this is probably you can calculate this value when you're conducting an experiment, right? This can be calculated from the raw data. And this is what we're going to be using in our 4th lab when we actually do an experiment, or you'll be using this in your capstone project, right? When you're actually conducting an experiment, you calculate this from your raw data. And this is the more practical. Again, this is the one that is going to be used most often in the real world scenario. So let's continue on with the NASA O-ring example. Let's say you're developing some sort of new O-ring for your space shuttle. Fail temperature, of your first batch is, let's say 12 degrees Fahrenheit. You have 13, and you do 10 of these. 9, so on and so forth. And then you use Excel, or you just, use the formula, and you calculate your standard deviation. And let's say, for the sake of today's calculations, your standard deviation, let's say you've optimized your process. Last time we had like a standard deviation of 1 or something. Let's say now you get your standard deviation down to, like, I don't know, 0.75 or something degrees Fahrenheit. The t-score changes. The t-curve changes with your sample size. When you're first optimizing a process, let's say you have a very small sample size, like 3, you're probably just going to get, all over the place, right? It's pretty much going to be a uniform distribution. Your curve of values is probably just going to be something, looks like this. But as you increase your sample size, your curve is going to, as you optimize your process, you're going to start getting, stuff over here. There's going to be more of a central, the central limit theorem essentially states that, you're going to start getting a pattern. And then as your sample size increases to, let's say, 10, what we're dealing with in the problem that I'm going to solve here, you start getting, more centrally located values. And let's say your curve starts, again, it starts looking more normal. And then finally, when you get to about 30, that's why we use that magic number of 30, it starts basically being a Z-score. It approximates a Z-score. Now, you're going to want to get it, as it approaches infinity. Obviously, that's when you get a perfect Z-score. But, as we'll see in the chart today, when you start getting to like 200, it's basically identical to a Z-score. But you're not going to see too much change here as you keep going. It's just going to be a little bit more central. But the change happens fast at the beginning and slower at the eventually evolves into a Z-score. But when you have smaller sample sizes, you have to use this t-score distribution. And as we're going to see, it's a different chart because of that, right? It's changing. And so the way you read that t-score, so let's come up with an actual problem here. So let's say you're estimating the fail temperature, just like from before, right? What is the 90, let's say, we haven't used, let's use 95 because we're going to get a different value. So what is the 95% confidence interval for this information here? Sample size 10, standard deviation 0.75. All right. So I just want to point out one term before I go to the next here. Next slide is this term here, point estimate. I didn't mention it yesterday. You might have seen it on the slide deck because it's the same for proportions, but a point estimate is a fancy word for whatever the sample mean is. So you're going to see that in the Pearson questions as well. They'll say, what is the point estimate? The point estimate is always just your sample statistic. It's basically your best guess. It's what you put error bars onto. So the point estimate is going to be either your sample average or your proportion of the sample proportion that error bars are added to. It's just a fancy term that you see. It's just a fancy word of saying sample average or sample proportion. So the first thing you have to figure out here is what is your alpha value? So again, recall from yesterday, alpha represents the total uncertainty in a confidence interval or in a hypothesis test that we do in chapter 8. So for a 95% confidence interval, your alpha value, the total uncertainty, would be 5%. And as you can see with a confidence interval, again, the uncertainty is divided into two, right? Because there's a low error, and then there's also a high error. And so it can fall into one of these two categories. But with this, and this is the important part, listen here, this is a confusing diagram because you're still going to use the alpha value. So for confidence intervals, these are what are called two tails because the uncertainty is divided in half. But when you look at this chart, again, when you look at the chart, it's confusing because this is still the alpha value. This is still alpha. They don't write that on there. I would have assumed, if I didn't know any better, and this is the mistake that students make, because I would make the same mistake. If it was just me looking at this chart, I would assume that this is alpha over 2, but it's not. It's alpha. So your alpha value that I'd be looking for, right, 5% is the same thing as 0.05. You're going to use this value here. This is the total uncertainty for two tails. So that's what you want to use with a 95%. Again, it's a little confusing. Here they divide it in half if it was a one tail, and again, it's a little misleading. We're going to only use one tail in chapter 8. This is for hypothesis testing when you want to know if something's bigger or smaller than it was before. One tail is only chapter 8. So when we talk about that next week. But for now, let's just focus on two tails for confidence intervals. So always put your alpha value. Again, it's both of these are alphas. This one too. Okay. Hopefully that makes some sense. Okay, so two tails because it's confidence, and this is a 95% confidence. All right. Now, degrees of freedom is the next thing we have to figure out. So a degree of freedom, and I talked about this, I believe, in chapter 3. This is why this course is cumulative, because you have to keep recalling these things from chapters previously. A degree of freedom, in this case, is going to be your sample size minus 1. So if you have a sample size of 10, like we do in our problem, your degree of freedom is going to be 9. And so you would go here and you'd say, all right, 0.05, degrees of freedom 9. And so this is our T-score here that we're going to use. 2.262. All right. And again, the way we found that was alpha 0.05, two-tail, and our degree of freedom is 9. And now we can calculate the error. So let's use our formula, right? So this is, kind of step 1, I guess. Step 2, label your steps so that I know where to give you marks. Right, let's calculate the error. .75 we decided would be our standard deviation, square root 10. All right. Calculator time, 2.262 times 0.75 divided by the square root of 10. So here my error is 0.5365. What is the 95% confidence interval for the O-ring failure with a sample size of 10? So over here, sample size of 10, standard deviation of 0.75, and yeah, what is the 95% confidence interval? So the reason the reason we're using T-scores is because of a small sample size, and we don't know the population standard deviation. We only know the sample standard deviation. So we can't use the central limit theory to approximate for a Z-score, and there it is. That's pretty much the setup there. Does that clarify things?
Yes, thank you.
All right. So we would say, right. So what's our answer? Well, our answer is going to be in this form, right? We're going to say this is what we've been trying to figure out, right? Take your point estimate or take your sample, throw in some error bars. We know the error. We know the average. We decided it's going to be 11 because that was the failure of the, again, of that. I keep using that example from the space shuttle launch because I find it fascinating. Let's actually, sorry, maybe I didn't mention that. Let's say the average is 11. But you would calculate that from your raw data as well, right? Let's say your average is 11. The error, and so you can give your upper limit, right? The upper limit on your confidence interval would be 11 plus 0.5365. And your lower limit minus your error let's just use 3 digits maybe for because of the significant digit issue. This is 2 digits, so let's just use 3 digits here. Let's go 11.4, or let's go 11.5, and let's go 10. So I guess this would be 10.5. Yeah, if I had to round that, 5.3. Yeah, it'd be 10.5. 10.4. Oh, hold on. It's too early. It's too early in the morning for me to be doing all this mental calculation here. 0.5365. So that's 10.46. 4635. So if I rounded to 3, that would give me 5. Yeah. Okay. All right. So what would you say? Well, again, this is where we want your conclusion. You know, what's the answer that you give your boss? Right? Your boss is going to be like, how's that O-ring process going? What's your average fail temperature? This is the answer you would give. You say the fail temperature of the O-rings, the actual fail temperature, or the true fail temperature, whatever you want to call it, is between 10.5 and 11.5 degrees Fahrenheit. How do you spell Fahrenheit? Let's take that. I knock you guys for spelling, so maybe I should look it up. Fahrenheit, with an H, Fahren. The Americans and their Fahrenheit scale. I don't know why they just don't abandon it and get onto the metric system like everybody else. But there you go. 10.5 and 11.5 degrees Fahrenheit. And then what's the missing part here is you have to state the confidence, right? The error without confidence is meaningless. So you would say 95%, or if you read the newspapers or other publications, they'll always say 19 times out of 20. Just because 95% is the standard. You'll hear this all the time, 19 times out of 20. So make sure you state that, or else again, it's meaningless without giving the confidence. So once you've got your error bars, the next thing you're going to want to do is deal with, how do I estimate the minimal sample size to get an error that I'm actually comfortable with? So if you actually know the acceptable error, then what you can do, so again, this is for means. We'll look at the proportions on Friday, but we can deal with this one right now, is if I know what my population standard deviation is, and I know the acceptable error, then I can calculate what sample size I would need to get these values here. This is a very important application. It might be the most important application. I know I've said this a few times, but it's only because this course gets more and more important. But this one is so practical, right? Because think about it when you're as an engineer or a project manager, or just as a human being in general, you want to do the least amount of sampling, right? Because sampling takes time. Samples are expensive, especially testing O-rings, right? Sampling is expensive and time consuming. And that's why companies always get into trouble, is because it's expensive, so they don't do enough of it. Let's say, again, just to kind of continue on here, let's say your boss came back to you and said, look, this is too big of an error. This is pretty good. This is like, plus or minus 0.5 degrees off your point estimate. But let's say, and this is a great follow-up question, your chief engineer comes up to you and says, look, we need an error that is no more than 0.1. Your standard deviation here, what is it? Currently we said it's 0.75. So let's keep it that. Let's keep it 0.75. Because this is what, so let's say that now we can keep this the same, right? This is our sample standard deviation, but let's assume it's going to stay the same as we increase our sample size. Right, as you optimize your process, your standard deviation should decrease. But for now, let's assume that we've optimized it. This is as close as we can get it for now. So without changing it, we'll assume that's going to be the new. If we made 1 million of these, it would be the same. Now the question is, let's use a new ZScore. Let's say we want to be 98% confident. So the question would be, again, I just kind of wrote down the numbers here, but on your quiz or on your test or in Pearson, the way it would be stated is this. what is the sample size needed, or what is the minimum sample size needed? Minimum and sample size is kind of the same. So let's just say, what is the sample size needed? Or how many O-rings must you test to get the error on the mean within 0.1 degrees? Assume 98% confidence. And again, as we were talking last time, it's probably going to be 99 or 100 in a real world scenario, but let's use 98. Let's use 98 for now, because you see these numbers a lot in this course. 98%, let's look up that Z-score, because that's the only thing missing here, right? We know the error, we know the standard deviation, we need to figure out our confidence. This is the only new thing. So we're not using T-scores here, we're using Z-scores, because again, we're assuming that as your process increases, it's going to be the same. So we can use the Z-score. So 98% in the middle that means there's 1% here. 1% there. And so we need something with, we have to look up a Z-score that corresponds to 0.001 or just 0.01. And again, this is a very popular one. You'll see it a lot on your Z-score chart. Or just you'll see it a lot in your life in this statistics course anyways. And I think as you know, as actually Saeed was bringing this up at the end of last class there, you know, if you actually need to be more than 99% sure, use this Z-score here, right? If you want to be like 99.99%, which is the top of our chart here, you might as well use, you know, if you want to be super sure, use 3.49 or something as your Z-score to be. But again, the questions you'll see for the purpose of this course, it's to the nearest percent. Some people are going to make this mistake. They're going to look up the wrong value. They're going to look up, you know, something like this. Right? Make sure it's not, you know, it's not that one. Make sure you get your decimals right. All right, 0.01. So this Z-score is also very famous. So this Z-score, alpha over 2 of 0.01, or I guess 99 according to that critical score thing, would be 2.325. So this is the one you use for 98% confidence intervals. Right, this is the critical value to the right that we learned last week. But this is a popular one. If you want to be 98% confident using Z-scores, there it is. 99, this was the 99 one. But again, just be comfortable using this table because, you know, on your test, the final exam last year, I think they used like, you know, 82% confidence. You know, make sure you're comfortable looking them up. All right, so there we go, 2.325, and we're in business. So step one, I guess, was kind of what I started with. What do we know? Step two, what is the Z-score? Well, here's your diagram. So we're going to use 2.325. Step 3, do the calculation. $304.06 dot dot dot. We always round up when you have a sample size because it's a discrete value. Always round up with discrete values when you get a decimal. Chapter 1 coming back to haunt you. So 305 O-rings need to be tested with the current process as it is.